കേൾക്കാവോ? ഹലോ,
ഹലോ.
കേൾക്കാൻ പറ്റുന്നില്ലേ? ഓക്കെ ഓക്കെ.
കേൾക്കാം.
തുടങ്ങട്ടെ. Today we are discussing differentiation under the integral sign. So in the last class we have discussed the interchange of integration technique, and we have discussed 2-3 theorems, and I think you have already done 2-3 examples. So now we move to the differentiation and integration. Okay, it is a very important section because sometimes we have to use differentiation under the integral sign or interchange of integration and differentiation. Everything we have to do in our daily analysis. Okay, so in this section we consider a function, a multivariable function f of x1 x2 xn is a real valued function defined on D subset of R is n. If some of the xi's, that means xm plus 1, xm plus 2, etc. xn are integrated out, we obtain a function that depends only on the variables x1, x2, etc. xm, that means remaining variables. So we have to understand how to integrate with respect to xm plus 1, xm plus 2, etc. xn when we have n number of variables. So that type of techniques are discussed here. Okay, so let us consider this theorem, and D is a function from D to R where D subset of R2 that contains two-dimensional cell C2AB. You know what is a two-dimensional cell? That is C2AB is nothing but a cell that consists of points in the region A1 less than or equal to x1 less than or equal to b1 and A2 less than or equal to x2 less than or equal to b2. Suppose that, for example, I will show you that region. I think we have already discussed that region in detail, no problem, so I am skipping that. Suppose that f is continuous and has a continuous first order partial derivatives. So this is the basic requirement, okay, for the interchange of integration and differentiation. What is the condition? F is continuous and has continuous first order partial derivative. So that is a minimal requirement for the interchange of integration and differentiation with respect to x2. So suppose that f is continuous and has a continuous first order partial derivatives with respect to x2 in D, then for A2 less than x2 less than b2, yeah, we can see that d by dx2 of integral a1 to b1 f of x1 comma x2 dx1 equal to integral a1 to b1, then differentiation comes dou f of x1 x2 by dou x2 dx2. Here we have used partial differentiation notation because we have two variables and we are differentiating with respect to x2 only. So that is the reason for considering this partial derivative symbol. So this is the result. That means a derivative of the integral equal to integral of the derivative. Derivative of the integral equal to integral of the derivative. What is the condition? Yeah, condition is nothing but f is continuous and has a continuous first order partial derivative. So remember that point. F is continuous and has a continuous first order partial derivative with respect to x2. So that is the minimal requirement for integration and interchange of integration and differentiation. Okay, let us go to the proof. It is a very simple proof. If you have idea about continuity and differentiability, then it is very easy to prove. Okay, let h of x2 be defined on closed interval a2 comma b2 as h of x2 is equal to integral a1 to b1 dou f of x1 x2 by dou x2 dx1. So this is h of x2. Okay, we have given that we obtain already the in theorem we have the result that the partial derivatives are continuous, that is dou f by dou x2 is continuous with respect to x2. Okay, so that information can be used here. Since dou f by dou x2 is continuous, then what is the lemma in this previous section? We know that if it is continuous, then the integral will be continuous. So that is the I think that is the last result we have proved. Last but one. In the last but one class, we have proved that result. I think. Yeah, I think this is that result. Okay, what is the result? Suppose that f is a real valued continuous on C to AB, then g of x2 is continuous. So instead of f of x1 x2, we use dou by dou x2 of f of x1 comma x2. So since dou f by dou x2 is continuous, here in this theorem it says that f is continuous. In our problem, instead of f we use dou f by dou x2. So since that is continuous, this g is also continuous. So that is the result we have discussed in some of the last class, and we will use that result here. Okay. So yeah, dou f by dou x2 is continuous, then h of x2 is continuous on close to a2 comma b2. Okay. So now let us take a variable t such that a2 less than t less than b2. Okay, we can integrate h of x2 over the integral a2 to t. So what happens? That is given here. Integral a2 to t h of x2 dx2 equal to integral a2 to t. What is h of x2? H of x2 is given here. We can substitute that here. Then integral a2 to t, integral a1 to b1 dou f of x1 comma x2 by dou x2 dx1. Okay, so substituting that result, we will get this one. Okay, so okay, again we have discussed one another theorem, that is order of integration can be changed. That is discussed in the last class. Okay, order of the integration can be changed. Yeah, I think yeah, this one is the generalized Fubini's theorem, and before that, yeah, this one, Fubini's theorem. We have discussed the condition for interchange of the order of integration. The requirement is f is continuous. So instead of f, we have dou f by dou x2. So that result can be applied here, and we will get order of integration can be reversed, and so after interchanging the order of integration, we will get this result. Integral a1 to b1, again integral a2 to b2. Here it was at the first, integral a2 to b2. Here it was in the second. Okay, so second question. So integral a2 to b1, a1 to b1, integral a2 to g dou f of x1 x2 by dou x2 dx2 dxn. So we have interchanged the order of integration by applying the Fubini's theorem due to the continuity of dou f by dou x2. Okay, the requirement is dou f by dou x2 is continuous. So that can be applied to the mean value theorem. So what is the mean value theorem says? Yeah, this one is similar to the mean value theorem. What is that? Integral a1 to b1. So instead of this bracket, we can substitute this one. Okay, this is the application of mean value theorem. What is mean value theorem? You know what is mean value theorem? Yeah, mean value theorem says that capital F of b minus capital F of a equal to integral a to b small f of x dx. So that is the mean value theorem. So instead of integral a to b small f of x dx, we use capital F of b minus capital F of a. So that is the mean value theorem. So mean value theorem is applied here, and we obtain that integral a1 to b1 f of x1 comma t minus, because the integral value of this one is nothing but, what is that? Yeah, that is this is derivative. So capital F will be small f here. Okay. So I will show you that after opening the Microsoft Word. I will show you that step, or otherwise we can take from the book of Bartle. Book of Bartle. I think that is available. You know the mean value theorem. Okay, conditions are there. Continuous in the open interval, differentiable in the continuous in the closed interval and differentiable in the open interval. So I will show you. No problem. So what is the mean value theorem? Yeah, mean value theorem says that f of b minus f of a equal to integral a to b df by dx. Okay. So this what are the condition? What are the condition? Yeah. It can be treated as
identity card and they don't question printed
okay. So this is the mean value theorem where f is considered to be integrable and capital F is differentiable. So all those theorems, all those results can be viewed on this book of Bartle. Okay, mean value theorem. Mean value theorem. These are some mean value theorems. You know that we are using this theorem. Yeah, f of b minus f of a equal to f dash c into b minus a. Okay, f dash c into b minus a. Or we can integrate. Yeah. ഒരാളുണ്ട് ആ പൊട്ടിച്ചോ ആ we have some other theorems also. So I think this is the as a continuation of this mean value theorem, you can see in the Riemann theory of integration technique, first fundamental theorem. Is it available in this Riemann theory? Yeah, I think this is the Riemann integral. Yeah, first fundamental theorem. What is the first fundamental theorem? There are several theorems we have to discuss simultaneously, and using that theorems we can, this fundamental theorem. You can see this is the result we have used. Fundamental theorem. This is a continuation of that mean value theorems. Okay. So as we seen in this theorem, so we have result that, what is the result? Yeah, instead of integral a to bt dou f by dou x to dx, we can write f of x1 x1 t minus f of x1 a2. Okay, is similar to this theorem. This result. Okay. So that can be separated into two functions, a1 to b1 f of x1 comma t dx1 minus a1 to b1 f of x1 comma a2 dx2, that is f of, that is, it is a notation only. Okay, f of t minus f of a2, f of t minus f of a2, where f of y is equal to integral a1 to b1 f of x1 comma y dx. So this is only notation. Okay, as we seen in the fundamental theorem, it is a notation only. So if we now apply the theorem and differentiate two sides with respect to t, we obtain h of t equal to h dash of t, that is. So yeah, this is fundamental theorems. Okay, this is fundamental theorems. So let me show the second fundamental theorem. What is second fundamental theorem? It is available in this book. Okay, this one. This one definition is given. Okay. Yeah, second form. What is the second form? Yeah. What is that? F is continuous at the point and definite integral defined by the differentiable in f dash of c. F dash of c equal to f of c. So f be continuous at the point c, then indefinite integral defined by 3 is differentiable at c and f dash of c equal to c. So that can be applied here. And okay, let us look at the theorem 6.4.8 in this book itself. 6.4, that is actually fundamental theorem. 6.4.8. 6.4.8. Yeah, this one is the theorem. It is, this is the fundamental theorem combined together. Okay, this is exactly, suppose that f is continuous on plausibility AB, that f of x equal to, as we have denoted, then we have the following: dou f by dou x equal to f of x, and integral a to b f of x dx equal to gb minus g of a. So that is applied here. Okay. Yeah, that is moreover, this we can substitute here. What is h exactly? What is h exactly? This is x. Okay. So h of x2 equal to f dash of x2, or h of t equal to f dash of xt. Okay. So what will be the result? Instead of h we use h of t we use this one. This is h of t. The left side is h of t. This is capital. The term integral is the capital F of t. Okay, we can see from here. So instead of h of t we used this one, and instead of f dash t we used the d by dt of capital F of t. So we hope we obtained the result. What is that? Integral of derivative equal to derivative of integral. So that is the result of this theorem. So what is the result exactly? Yeah, we have a function f continuous, and as a continuous first order partial derivatives with respect to x2, then d by dx2 of integral a1 to b1 f of x1 comma x2 dx2 equal to integral a1 to b1 dou f of x1 comma x2 dx dou x2 dx1. So interchange of integration is attained. So we obtain that what is that? H of t equal to f dash of t. Equivalently, instead of h of t we call it as integral a1 to b1 dou f of x1 comma t by dou t dx1, that equal to d by dt of capital F of t, that is d by dt of integral a1 to b1 f of x1 comma t dx1. So that means interchange of integration and differentiation is possible for every t. What is the range of t? Range of t is nothing but a2 less than t less than b2. So for any number in between a2 and b2, that is a t is only a variable. So for any variable value in between a2 and b2, we can interchange the integration and the differentiation. So required condition is f is continuous and it has first order continuous partial derivatives. So we have proved the theorem, and so I think this is sufficient for today's session, because it is already we have 9, 10, and we have to discuss another theorem, that is a lengthy theorem. So before that, you may discuss the Lagrange method of integration. Sorry, what is that? Lagrange's multipliers. So this is the session of Lagrange's multipliers. So that is required for this formula theorem. Okay.